Good morning, ladies and gentlemen. Today we are going to work on Chapter 15, Section 8, Probability with two or more activities. The first part of this section is going to seem kind of a review-ish. We've seen some replacement issues with marbles and some of the problems you did in 15.7, but we're going to go over it formally now. When doing probability, there are two issues you need to be aware of, and that is whether or not in multiple rolls of a die, or if you're pulling more than one card out of a deck, whether or not you have to replace the things. Okay, with rolling a die or spinning a spinner, things have to be replaced because you're not going to actually take a side off the die. You're not going to remove a sector of the spinner. So some things are automatically replaced every time, but things like cards, pulling marbles out of a bag, you don't have to replace the marble. You don't have to replace the card, so you have to be smart about that stuff. Alright, let's take a look at our example here. Two cards are drawn from a standard deck of cards. We want to draw two kings and we're not replacing them. So for our first pull, there are 4 kings in the deck out of a total of 52 cards. And we take that card out and we're not going to replace it. So you have to think to yourself, okay, so say I get the king of hearts. How many kings are left in the deck? So we had 4, we took one out, we set it aside. There are 3 kings left in the deck. There is not 52 cards anymore in here either. That's another thing that you have to be aware of. Yeah, there's 3 kings, but there's not 52 cards. You've taken a card out, you set it aside. There is 51 cards left in the deck. So you'll notice I loaded up the calculator here. 4 times 3 is 12, so I don't need the calculator for that. But 52 times 51 is a pretty big number. And I get 2652. So 12 over 2652. And this is a good time to remind you how you can reduce fractions on the calculator. If you do 12 divided by 2652, you're going to get a decimal. We don't want to give that decimal as our answer, but if you hit the math button, which is right underneath the alpha key, you notice we have this little arrow frac. Arrow frac is what you want. Right here, arrow frac, right there. And it will automatically be highlighted. So all you need to do is hit the enter key, hit it one more time, and 1 out of 221 is the reduced answer. So 1 over 221. Alright. It says here, dependent events, remember to assume you get it first. If we assume that, or if we open up the possibility that we don't actually get a king on the first pull, the whole problem falls apart. So when we're doing these probability questions, you're going to always assume that you do in fact get the number you want. And that's going to lead to the answer that you're looking for. Okay. Let's take a look at the same problem if we actually take the card out, take a gander at it, enjoy its beauty, and then put it back in the deck. And then we pull another card. So we want to draw 2 kings while replacing it. Well, there's a 4 out of 52 probability of getting a king when you pull a card out of the deck of cards. You put the card back in, the probability of getting a king on the second pull is exactly the same. So we get 4 out of 52 times 4 out of 52. 52 times 52 is 2704. So 2704 for the denominator. 4 times 4 is 16. Okay, once again, we can reduce this fraction by doing 16 divided by 2704. Get the decimal, hit math, and then hit enter 2 times. So 1 out of 169. If problems don't specify, you must ask yourself, does this situation imply with or without replacement? For example, if I tell you that you have a pizza, you eat a slice of the pizza, and then you go back and have a second slice, it's kind of obvious you're not replacing the slices because they're in your belly. But the directions won't tell you that it's without replacement. So sometimes you got to figure it out. Once again, a die is always with replacement. A spinner is always with replacement. There are certain things where you can't take the item you took or got for the first roll or spin or whatever and remove it. It's just not possible. So if you're eating M&Ms out of a bag, you're not going to have replacement. You ate that M&M, it's gone. Alright, conditional probability. It's a favorite of the Regents exam. It's kind of spicy. Let me explain here with our first example how it works. If you had to reason it out without using the formula, and you do see the formulas given here, here's how you would think about it. I want to get a 4, but I know that I rolled the dice and my friend like covered up what it was. I know that from the outcomes on that die, that my outcome was an even number. Now, I don't know which even number it was, but it was an even number. So I know I didn't get a 1, I didn't get a 3, and I didn't get a 5. I got an even number. So there are 3 possible outcomes, one of which is the 4, and this answer becomes 1/3. That's kind of how it works. It's a little bit tricky to do it using logic, so we have a nice formula for it. For problem A here, we would make this the probability of getting a 4 and an even, and we will divide that by, or really make our outcome, the probability of getting an even. So we can do this like an and ands can be reasoned out, but I'll actually do it formally here. The probability of getting a 4, okay, there is one outcome. The probability of getting an even, that's 2, 4, and 6. Alright, so the probability of getting a 4 and an even is 1 out of 6. The probability of getting an even when you roll a die, as you can see here, is 3 out of 6. So in order to divide fractions, we have to take the second fraction, flip it over, and multiply. You get 6 out of 18, which is 1/3. And that's how you do conditional probabilities. They're tricky. Probability of 1 given less than 5. So you want to take the probability of getting a 1 and less than 5 divided by the probability of getting less than 5. Now once again we're rolling a die. So the outcomes when you're trying to get a 1 on a die would just be 1. The outcomes when you're trying to get less than 5 would be 1 through 4. Okay, and remember for and they have to satisfy both conditions. So the probability of getting a 1 and less than 5 only happens one time. So this would be 1 out of 6. Okay, the probability of getting less than 5 is 4 out of 6. So the way we do 1 divided by 6 divided by 4 divided by 6 is to flip and multiply. We flip the bottom fraction over and we multiply. You get 6 out of 24, which is 1 out of 4. Okay, that's the answer to this problem. Another way to think about it, listen, this is not easy. I'm not pretending that it is. Another way to think about it is I know that I got a number less than 5. So I got, for my outcomes, 1, 2, 3, and 4. My denominator of this answer is going to be 4. What's the probability of getting a 1? Well, how many 1s are there? There's just the 1. 1 out of 4 is the answer. So you can use logic to do the problem. It's just very tricky logic. And the formula is fantastic. They love to test this on the Regents exam. Oh my goodness. Okay. Now, 2 cards drawn from a deck, probability of getting a pair. This is a conditional probability, but it's way easier to just kind of logic and reason it out. If I'm trying to get a pair, I don't actually care what the probability or what kind of card the first card is. So the probability of actually getting a card when I pull a card out of a deck of cards is 1, because I absolutely will on the first pull get a card. You look at that card, you know what it is, you're not going to replace it. You know there are actually 3 cards left in the deck that have the exact same picture on it, except they're different suits. And there are 51 cards left in the deck. So this becomes 3 out of 51. Alright. Sometimes you have situations where you don't care what you get on the first pull or on the first roll. And when that happens, we just make it 1. We just don't simply care what the first one is. After that we care, and then we start working out those probabilities. Okay? Well, let's see. 351, that reduces, 3 goes into 5 once, remainder 2. That would reduce to 1 over 17. Alright, coming down here. A jar contains 4 white and 2 blue marbles. Marbles drawn by random and not replaced. Note that, not replaced. A second marble is drawn, so both white. There are 4 white out of 6 marbles. You take one of the white marbles, you throw it away. There are 3 marbles left and only 5 marbles remain. We multiply them together and get 12 out of 30. And that's 2 fifths. There are 2 blue marbles out of 6 at the start of this. We take a blue marble, we throw it away. There will be 1 left and 5 marbles left. This gives you 2 out of 30, which is 1 out of 15. Both the same. So we can rewrite this. This is the probability of getting white and white or blue and blue. Well, we figured out white and white in part A. It was 12 out of 30. I'm using the not reduced answer, so I have a common denominator here. Blue and blue was the part B answer, which was 2 out of 30. And this is an or. I don't care which one it is. I want one or the other. One or the other. I add them up, 14 out of 30. That's 7 out of 15. Look for those hidden ors. Notice C didn't say OR, it didn't have the letters right there, but that was definitely an or question. White, white, or blue, blue. Alright, let's see. 2 darts are thrown. We're going to draw a tree diagram. So for the tree diagram, on the first throw of the dart, I can get a 1, a 2, or a 3. This has to be replacement. You can't actually tear the dartboard apart for the second throw. So we're going to have 1, 2, and 3 are the same outcomes for the second throw of the dart. Okay. Well, now that I have my tree diagram here, I can actually skip doing some of the mathematics of this because I can just count them out of here. I know there are 9 outcomes. So I know my denominator for part B is going to be 9. So let's see, part B. Find both darts are the same. Well, that is going to be true when I have a 1 and a 1, which is right here. 2 and a 2, which is right here. 3 and a 3, which is right there. So 3 of my outcomes out of 9 have both darts that are the same. That's 1/3. The alternative would be to say, okay, what's the probability of getting 1 and a 1? That's 1/3 times 1/3, which is 1/9. What's the probability of getting 2 and a 2? That's 1/3 times 1/3, which is 1/9. What's the probability of getting 3 and a 3? That's 1/3 times 1/3, which is 1/9. And you could add them together. So that gives you 3 over 9, which is the same thing. But gosh, isn't it faster to use the tree diagram? For, what do we got here? For C, find probability of getting both odd numbers. Well, where do we have both odd numbers? 1 and a 1 are both odd. 1 and a 3 are both odd. There's not going to be any odd numbers in the middle, or I'm sorry, no, both odds, because it starts with a 2. 3, 1, 3, 3. So for C, 4 out of the 9 have both odds. They are 1, 1, 1, 3, 3, 1, and 3, 3, in case you are curious where the 4 came from. Okay. P, at least 1, 3. Well, at least 1, 3. You got to remember that in our tree diagram, which I'm going to redraw here because I want to keep writing on it. Although, as you can see, getting a little sloppier. Try to keep it tidy for you. It says at least 1, 3. So we're talking about D here. Here's a branch with a 3 on it. So 1. Here's a branch with a 3 on it. 2. And all 3 of these, 3, 4, 5, have a 3 in it. At least 1. 3, 3 has 2 of them. So at least 1. So we go 5 out of 9. And D is done. Okay. Last but not least, for E, we're going to figure out the sum is odd. So let's see. Let's write down all the sums. 1 plus 1 is 2. 1 plus 2 is 3, 1 plus 3 is 4, 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, and then I get a 4, a 5, and a 6. So of our 9 outcomes, which ones are odd? Well, 1, 2, 3, 4. So 4 out of 9 are odd, and that would be the answer to part E. 4 out of 9. Sometimes when it's a small number of outcomes, a tree diagram, might as well just use your tree diagram to help you answer the questions. Alright, number 5 here. Now we have 1,000 students, so we're not going to use a tree diagram for this. This would be ridiculous. A high school of 1,000 students, we have 300 play sports, 200 are in honors, 120 play sports, and are in honors. So this 120 are in 2 things. Find the probability of student who plays sports also is in honors. The probability that someone who plays sports are also in honors, well, look at, there's 120 students who do that, and there is 1,000 students total. So basically there's your probability right there. We can convert, or we can reduce this with the help of our magic mystery machine here. So it gives us 0.12, which is 3 out of 25. So word problem, but it's not a fancy one. If you play sports, you're also in honors. Okay. And let's see, we have anything else? 6, 1 red marble, 1 blue marble, 1 green marble, and 1 yellow marble in a bag. 2 marbles are drawn without replacing them. Find the probability that you get a red first. So there is 1, 2, 3, 4 marbles. So probability of red is 1 out of 4. Now, say I get the red. There's 3 marbles left. 1 of them are yellow. This would be 1 out of 12. To draw a tree diagram listing the ordered pairs, well, we got red, blue, green, yellow. And then on the second pull, the red is gone. So blue, green, yellow. For the blue one, red, green, yellow. For the green one, red, blue, and yellow. And for the yellow one, red, blue, and green. And you can see here, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 outcomes for that event. And that's it. Our last problem here is number 7. 2 quarters and 1 nickel in a pocket with a hole. Coin falls out, you put it back, so that means replacement. Another one falls out. Draw a tree diagram with list of sample space. So you could have the quarter fall out first, or the nickel. You put it back in, the quarter could fall out a second time, or the nickel could fall out. With your nickel as the first coin falling out, you put it back, the quarter could fall out next, or the nickel could fall out again. And that would be our tree diagram. For part B, the same coin falls out. So we're talking quarter, quarter, or we're talking nickel, nickel. That's 2 out of 4, or 1/2. For C, the coins total 30 cents. That happens here. 25 plus 5 is 30, and it happens here. So it's 2 out of 4, which is 1/2. The quarter falls out at least once. Well, keep in mind that your sample space is quarter, 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 nickel, nickel, quarter, and nickel, nickel. So how many of these have at least a Q in it, at least one Q? 3 out of 4. And that's the answer for number 7. Alright, we're done. We're going to be on 624 tomorrow, 3 through 11, so not a terribly long assignment. I look forward to seeing you tomorrow. Have a great evening.